Let's look at the following problem. The acceleration due to gravity at the north pole of a planet is 10 meters per second squared. The planet's mass is 6 times 10 to the power 24 kg, and its radius is 6.4 times 10 to the power 6 meters. It makes one revolution about its axis in about 24 hours. Find the gravitational force on a 4 kg object at the north pole of the planet. So when the object is at the north pole of the planet, what is the gravitational force or the weight of the object at that location? Part B. What is the apparent weight of that 4 kg object at the equator, and therefore the acceleration due to gravity at the equator of the planet? Let's do a rough sketch. Let's assume that is the planet and that is the equator line. For simplicity, let's assume that that is the axis of rotation, so the planet rotates like that, about that axis. The problem asks you to specifically compare the gravitational acceleration at the North Pole versus the equator. Why the values should be different? Note that this planet is spinning about the axis like that. Let's look at a free body diagram of that 4 kg object when it is at the North Pole. Of course, it has its weight, let's call it W, and a normal force from the ground, let's call it N. Because the object is exactly on the axis of rotation, the effect of this rotation can be ignored. Of course, if we treat this object as a point particle, then its spin, its bodily spin about the axis can be ignored as well. So because the object is not moving anywhere, we can write immediately normal force equal its weight. So for part A, we are looking for the gravitational force or weight of that 4 kg object at the North Pole, and that is quite simply the mass of the object, 4 kg, times the gravitational acceleration at that point, which we are given, 10 meters per second squared, right there. And the answer is 40 newtons. Now for part B, we are interested in the weight of that 4 kg object at the equator. So let's assume we are looking at the object placed here. Of course, its weight will go towards the center of that planet, let's call it W. You have this normal force from the ground going in an opposite direction. In addition to that, because this object is part of that circular motion of that planet, you should have a centripetal acceleration towards the center of the planet. So this A sub c is the centripetal acceleration of this object towards the center of the planet. Centripetal acceleration indicates the presence of centripetal force, which is a kind of net force. So the centripetal force must be supplied by something. In this case, there are 2 forces that can supply to the centripetal force. It is indeed the combination of them. So because the centripetal force is going that way, that means the true weight of the object minus the normal force on the object is indeed the resultant force and is indeed the centripetal force on this object. We know the centripetal force is given by the mass of the object times its tangential speed squared over the radius of that circular trajectory. Putting everything together in this equation, we get mv squared over r equals w. W is the true weight of this object. So the true weight is given by part A, namely the weight at the North Pole. So let's call it 40, which we have already calculated there, minus capital N. N is the normal force, and N is what we call the apparent weight of the object at that location, which is what we are interested in. Before we proceed further, we should point out the resemblance of this system to the elevator system. Remember the elevator system where you have a person standing inside in an accelerating elevator. So in this case, let's assume the elevator is accelerating downward with an acceleration a, and the mass of the person is, let's say, m. So the free body diagram on this person at this moment can be sketched as follows. So you have the true weight, and then you have this normal force from the ground or from the floor of this elevator. And if you want to write Newton's second law for this system, because the acceleration is downward, the net force is downward, we say W minus N equals ma. Do you see the resemblance of this equation with that equation, with mv squared over r taking the place of ma? So just like in an elevator system, the acceleration creates an apparent weight of this person. The rotation of the Earth creates an apparent weight of this object due to its location at the equator. Let's get back to this equation. What is r? R is the circular trajectory radius. In this case, that radius is the radius of that planet, and we are given that number. It is 6.4 times 10 to the power 6 meters. So r is 6.4 times 10 to the power 6 meters. What about the tangential speed of the object? The tangential speed of this object that moves in that circular orbit is the speed of the rotation of the Earth at the equator. And that can be determined easily. It is just the distance covered by this object in one revolution, that is just 2 pi r, the circumference of that orbit, divided by the period of rotation, which in this case is 24 hours. So hours turn into seconds. You multiply that 24 times 3600. We note this r here is given by that number. Calculating v, you get 465.42 meter per second for the speed of that rotation. Substituting this number in here, and we know the mass of the object is 4 kg, so little m is 4 kg, and this capital R is again that number, we can calculate capital N, which is the apparent weight of that 4 kg object at the equator. And N will turn out to be 39.86 newtons. And that's the answer for the apparent weight. Having found the apparent weight, we can use that to determine the acceleration due to gravity at the equator of the planet. And how do we do that? Since the weight or the apparent weight at that point is 39.86 newtons, that is quite simply equals the mass of the object, which is 4 kg, times the gravitational acceleration at that point. Let's call it g prime. And you can get g prime. And when you do the calculation, you get 9.965 meter per second squared. You can obviously see the difference between this value and 10 meter per second squared at the North Pole, and the difference is due to the rotation of the Earth. And that solves the problem. Thank you for watching.